All right, welcome to part 2 of limits involving infinity. Here I want to look at this function y equals sine x over x. In the previous video we talked about a horizontal asymptote being defined as the y value that the function approaches as you move either to the right on the x-axis or to the left on the x-axis. This function is a good demonstration of a function that not only crosses the horizontal asymptote, but crosses it an infinite number of times. And so sine x over x, if you want to graph it in your calculator, you probably get or on Desmos, so you get a better picture of it. But sine x over x is going to start up here at 0, 1, although 0, 1 is actually undefined, but it's an open, it's a hole in the graph, and it's going to oscillate up, over and below the x-axis repeatedly, okay, forever. But what happens is the y values get closer and closer and closer to 0. So we still have an asymptote here because we have the limit as x approaches infinity, or positive infinity, of sine x over x is equal to 0. Okay, so there is a horizontal asymptote at y equals 0. And we can use this fact to solve other problems, all right? And the properties of limits that we learned previously that applied to limits at certain values, like the limit as x approaches 6 instead of infinity, those properties apply to the limits approaching infinity as well. So, for instance, we can solve problems like this. The limit as x approaches infinity of 5x plus sine x divided by x. We can solve this kind of problem by using the properties of limits that we learned in earlier on in the unit. Okay, so let's do that. I have 5x plus sine x over x. I want the limit as x approaches infinity, so I'm going to do some algebraic manipulation to this expression and see what happens. So I have the limit as x approaches infinity of 5x over x plus sine x over x. Now I'm choosing to break this fraction up because I don't have a lot of other options for algebraic manipulation here. I can't go for a common denominator. I only have one fraction. I don't need to combine fractions. There's really not a lot that I can do to this except break the fractions apart, or break it into two fractions and hope that something simplifies. Okay? And it does. So x over x here simplifies to 1 over 1. So I get the limit as x approaches infinity of 5 plus sine x over x. And so I can break this limit into the limit as x approaches infinity of 5 plus the limit as x approaches infinity of sine x over x. Well, now I can take these on each individually. Limit as x approaches infinity of 5, that's just 5, right? Because y equals 5 is a horizontal line. Limit as x approaches infinity will just be 5. So that becomes 5. And then the limit as x approaches infinity of sine x over x, well, we just talked about that one. That one's going to be 0. And so we get 5. Notice that I'm keeping the limit notation all the way through until I actually evaluate the limit, you can think of it as plugging in infinity, but until I evaluate the limit, then I can drop the limit notation. Okay, that's really important because otherwise you will have nonsensical statements, equivalency statements, as you go, and then you'll get the right answer with incorrect symbols up above. Anyway, please keep the limit notation until you actually evaluate the limit. All right, let's talk about vertical asymptotes real quick. Okay, we are not going to spend a ton of time on these because you should be fairly familiar with vertical asymptotes at this point. But let's look at, for example, the function y equals 1 over x squared. And let's look at the limit as x approaches 0. We'll start from the left, I guess, 1 over x squared. Okay. This graph is what I call a volcano graph. Again, you should try this one on your own before I do it here. Pause the video. right, so this is what our function looks like. And our question here is, what is the limit as x approaches 0 from the left-hand side, from the negative side? So the limit as x approaches 0 from the left is going to be positive infinity. You can see that the closer you get to 0 here, the further up the graph the y values go. You can see this in the table as well. It would be worth taking a look, but you can see that it goes to positive infinity. Right? So technically you might say that that limit doesn't exist either, but positive infinity is a more accurate description of what the function behavior is at 0 from the left. The limit as x approaches 0 from the right is the same. It's also positive infinity. The limit as x approaches 0 would then be positive infinity. Okay? So, I don't think we need to do those. Alright, and that kind of rounds out the limits at infinity portion. In the next video, we'll talk about end behavior and end behavior modeling.